Hello, and welcome to today's Vision Systems Design webinar titled Multiplex Imaging and Quality Inspection, sponsored by Accelitas Technologies. I'm Jim Tatum, Senior Editor of Vision Systems Design with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window, and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. Also, please be aware that today's session is being recorded and will be available on the VSD website within the next 24 hours. You will be notified by email when the archive is available. Now, I would like to introduce our panelists for today's discussion. Dr. Kavita Aswani serves as a Senior Application Scientist for Biomedical Products at Accelitas Technologies. With a PhD earned from the University of Iowa, she boasts an extensive background encompassing 7 years of scientific research expertise and over 24 years of applications experience in the fields of microscopy and fluorescence industry. Throughout her career, Dr. Aswani has contributed to numerous publications and peer-reviewed journal articles. Her specialized area of work include wide-field illumination microscopy, laser scanning microscopy, and flow cytometry. She remains an engaged member of both the Society for Neuroscience and the Royal Microscopical Society. Dr. Gerhard Holst graduated from the Technical University Aachen, Germany, with a diploma in electrical engineering in 1991, and went on to complete his doctorate at the University of Dortmund in collaboration with the Max Planck Institute for System Physiology in Dortmund, Germany, from 1991 to 1994. Dr. Holst furthered his research as member of the Microsensor Research Group at the Max Planck Institute for Marine Microbiology in Bremen, Germany, from 1994 to 2001. From 2001 to 2021, he was head of the Research and Science Department at PCO AG, where he was responsible for new technologies, research, and sensor projects, including the development of SCMOS image sensors. Since the acquisition by Accelitas in September 2021, he has become Senior Imaging Product and Application Scientist and is responsible for some of the advanced SCMOS camera systems, as well as the FD, FLIM, and SWIR cameras and research projects. Michael Bulk serves as the Group Product Manager of the Imaging Optics Group at Accelitas Technologies. He earned an MSc in Engineering Physics from McMaster University and has accumulated over 10 years of experience in the design and development of complex optical systems for industrial, medical, and defense applications. Thank you again to the three of you. Please proceed.
Okay, so I am Kavita Aswani. I am the Senior Biomedical Application Scientist with Accelitas Technologies. My expertise is more on the lighting side, and I will now have Gerhard, who is the expert in the cameras, and Michael, who is the expert in optics, gives you a brief introduction about themselves.
Sure.
Well, my name is... Go ahead, Michael.
Go ahead, Gerhard. No, you first, please.
Well, my name is Gerd Holst. I'm with Accelitas PCO since 2001, and my expertise is more in the field of camera technology and applications. And I'm a Senior Imaging Product and Application Specialist or Scientist.
And I'm Michael Bulk. I'm Michael Bulk. I'm a product manager for our imaging lenses. I'm based near our Munich office, and I've been with the company for about 7 years now. And I'll talk to you a little bit about some optical considerations for multiplex imaging. So thanks.
So we're going to discuss multiplex imaging in quality control. I will start with the illumination part. Gerhard will cover the camera part, and then Michael will come in for the optics. So overview of what we're going to talk about: multiplex imaging, which involves illumination, detection, and the optics in between. So let's start with discussing the spectral range. So spectral range is a range of the spectrum that can be used for investigations, whether it's fluorescence or reflection imaging. And this spectrum has actually been increasing because of advances in technology. We can go deeper into the UV and further out into the IR or infrared because we do have light sources, the optics, as well as the sensors and cameras that allow us to image or sense in this particular extended region. So, what is multiplex imaging?
Yes.
So, multispectral, hyperspectral, or multicolor imaging is used for absorption or reflection or multicolor fluorescence imaging. And we just wanted to kind of pull them all into one big pot and call them multiplex imaging. So, multiplex imaging can involve fluorescence images. And in fluorescence, the illumination goes from the light source to your sample, and the resulting fluorescence goes back to your eyepiece or to your camera. Apologies, you can't see my cursor, but hopefully you're following me on the right here with the fluorescence in the green arrow. For fluorescence, you can use either broadband excitation, which is basically a wide range of the spectrum, or you can use specific excitation wavelengths, which I will cover in the next slide. You have absorption or reflection, which again can use broadband illumination or different illumination wavelengths. Again, on the right here, you see the blue arrow going from the light bulb down to the sample. Coming out of the other end would be the transmission or the absorbance. And if it's reflection, it would go uh, back up north to your eye or to the camera. You can also have combination of more than one parameter. For example, if you're looking at the reflection, fluorescence, or absorbance, and you can combine them with your fluorescence lifetime imaging. And the resulting image can be either visualized through just contrast, or it can be analyzed by AI-based processes, which I believe Gerhard will cover a little more in detail. So for multicolor fluorescence, you have broadband illumination, which is a wide region of the spectrum, which is then filtered. In the multiband illumination, you would have separate LEDs or you would have separate lasers for a particular wavelength, and that may or may not require further filtering of the excitation light, depending on the wavelength of interest. The light gets through optics to your sample, back through optics. Here you do need filters to separate your excitation light from your emission. Goes to the camera. You get your different images. Image one, for example, would be blue, green, red, and your composite image would then give you information about all the three different features that you're looking at in one image so you can see where one is in relation to the other, which gives you some spatial information. For absorption and reflection, again, you could either have a broadband illumination or you could have multiband illumination with or without optical filters, depending on the requirement of the wavelength. Goes through your optics, gets to the sample. Here you will need optical filters because with the broadband illumination, you've hit the entire sample with every wavelength of light. Then you want to filter the emission, the absorption, or the reflection. And again, you end up with your image one color, image two color, image three color, and your composite image. If you then combine fluorescence or electroluminescence and other modalities, you would have your illumination, goes to the sample, gives you two images, which would be intensity. And then you can also get a lifetime image, and you can fuse the two to get more information about the sample and also the lifetime status related to it. Okay, so multiplex imaging applications, there are several of them. I will cover all of them one at a time when I get to them. But you can see that there's a wide range between, oceanography and documents, forgery, fake money bills, fruit inspection, art inspection, and several things like that. So we're calling this our multiplex imaging toolbox, where we have the light, we have the cameras, and we also have the optics that are required to perform multiplex imaging. So in your multiplex illumination, which is the part that I will cover, and then Gerhard and Michael will cover the camera and the optics. We discussed the actual spectrum. We do have light sources that go from UV to near infrared. And what's required for multiplex illumination? Multiplex illumination, so you could require a light source, obviously. This could be a broadband or a switchable light source. Again, broadband is where you have a very wide spectrum that you're hitting the sample with. Switchable is where you have individual parts of the spectrum, which are either LEDs or lasers. You will need to control the intensity of this light source. If you're doing fluorescence, you would require excitation wavelengths that would match the spectrum. This can be lamp, laser, or LED based. And again, depending on the application, you would require two of the lasers, or two of the LEDs to be able to excite simultaneously. If you're doing dynamic imaging, something very fast, you would require the LEDs or the lasers to switch fast between colors. Uniformity is always important because you want your data to be reliable and you want to make sure that you're hitting every part of the sample with equal amounts of light, and also repeatable amount of light over different time periods or different parts of your sample. So just to show you an example of one of our light LED illumination sources, it's called a Xylus 2. It has a wide spectral range. This is broadband between 360 and 750. There is a UV off mode built into all the systems. You don't require arc lamps anymore to go into the far red as you did in the past. And the green gap is something that LEDs suffered from when they were initially used. And what we've had to do to get a more powerful optical power between the 500 and 600 nanometer region, we've had to do a laser phosphor conversion, which we call our laser LED hybrid drive. For a switchable solution, there is the Excite Novum, which is multi-band. It has 9 colors in the that come out, 9 channels that come out of the box. This also has our laser phosphor conversion, giving you a very powerful that the big hump you see on the right in the graph there, that is the 500 to 600 using our laser phosphor conversion technology. And you can have filters inside this box if you choose to. So in broadband versus multiband illumination, essentially the difference is that in broadband, you definitely need bandpass filters in order to narrow down the spectrum because you're hitting it with a whole wide range of the spectrum of light. And in multiband illumination, you may or may not require the cleanup bandpass filters, but you would require a dichroic mirror. I am. So now that we're figured out what the light source is and how we're going to hit the sample, you would take your light, you would get it through your filters, through the sample, and then to the camera. So if you hit the sample with the top gray image here, you would get your red image, you would then get your green image, you would then get your blue image, all separate 3 images, and then you would fuse them into one. In this case, it's a bright field RGB image. And this example here is digital pathology, which is basically some cells that are being imaged under bright field. And traditionally, pathology has been bright field imaging. But if you add other biomarkers and you look at fluorescence of these biomarkers, you can get a more holistic view of the microenvironment and the cellular interactions that are happening between cells and between tissue compared to your normal RGB imaging. And here is an example of that. So on the right here, you see the bright field image. You can see the parts of the cell in gray. The green then is the fluorescence. And if you look at the far right image here, you've overlaid the bright field with fluorescence. And that gives you a lot more information about where certain molecules are targeted within the cell or the tissue. And that just gives you more information about how they're interacting, what's happening in a disease state versus in a non-disease state. And on the left here, if you use near infrared, you can actually get deeper penetration into tissue. You can get better signal to noise. And also you can get structures not visible to the human eye. So multiplex imaging, especially when combined with machine learning, you can get a lot more information classifying, for example, tumors. So on the left here, you see a mouse, and it looks just normal gray when you look at it under normal bright field imaging. But then if you hit it with some sort of fluorescence marker and you image it, you can then see, for example, a tumor that's highlighted. So the applications in biology are digital pathology. In the top image here, you can see the left part of it is just bright field imaging. And the right part of it, you can see a whole bunch of fluorescence markers combined with the bright field image, which gives you information about the location of molecules and how they're interacting in a disease versus non-disease state. You can also see that the fluorescence spectrum of certain molecules will change in diseased tissue compared to normal tissue. The bottom left here, you are seeing a surgical application. So there's deeper penetration into tissue when you use near infrared wavelengths. And in the left part of this bottom left image, you see the surgeon, and this is some organ within the body. The surgeon's illuminating it with just normal white light, where you can see the anatomy. But if you go to image B over here on the right, you can see that it has been infused with some sort of fluorescence. And in this case, the fluorescence is highlighting blood flow. So in the left part of the image, you see this wonderful green, which is showing there's blood perfusion, very good. But in the right half of that image, you can see that there's no blood flow. So that's giving you information about what's going on in the patient live during a surgery. Is this a sign of a stroke? Is it a sign of something else going on? And looking at this kind of information can also give you information on tumors, tissue oxygenation, um, and this will eventually help improve your surgical precision during a live surgery. On the right here, where you see this person's hand, you can see that the one of the fingers has been occluded with a rubber band. And if you look at it under multispectral imaging, in the middle and the right, you can see how that blood perfusion has been affected by the rubber band. In blood gas analysis, it goes beyond the visible spectrum and allows you to see components of blood far better than traditional bright field microscopy. And multispectral imaging is it's a non-invasive way of assessing blood gas parameters. And while it doesn't directly measure blood gas, it can provide information on what's going on in the environment, like the tissue oxygenation or your oxygen saturation, and it gives you more information about the blood gas status. Surgery, I briefly covered. Forensics is multispectral imaging can be used for blood stain detection, even on dark surfaces or after the blood has been wiped away. And this helps you give more information about the blood patterns and what may have happened during whatever crime it was that was committed. And you can also reveal hidden or erased tattoos on a person's body. So it's really another non destructive way of examining and handling crime scene evidence. In the materials world, your top left here, you can see the analysis of wood. In the top half of the image, you can just see a normal wood that you would see with a normal camera. If you then use multispectral imaging, you can see the defects in the wood. Same thing for the leather on the left-hand side. You can see under normal bright field imaging, and on the right, you can see the differences between genuine and artificial leather by using multispectral imaging. In the pharma world, which is your bottom left image, you can actually assess the composition of tablets even when they're enclosed or sealed. And you can see the variation in ingredients to check for uniformity or even for correct dosage. And you can see the package condition, you can see if the pills are broken, and you can see if the fill levels are good enough or if there are any foreign objects that should not be in there. For your semicon devices, you can inspect PCBs for structural abnormalities or surface defects. And if you use SWIR imaging or shortwave infrared, you can detect non-surface defects in semiconductors and solar cells because SWIR can see through silicon wafers and chips. There's also applications in your counterfeit detection, in your counterfeit, whether it's money or whether it's your passport or any other documentation. And this is because using multispectral, you can see the differences in ink composition paper quality and the security features. For artwork, you can see the difference between a real and fake piece of art because multispectral imaging can actually detect your subtle differences in pigments and materials. And like I mentioned, yeah, passports, licenses, certificates. By using multispectral imaging, you can see subtle differences that you cannot see by the naked eye. Lastly, I'm just going to cover the food industry, which is actually very interesting. For example, here you can see, if you look at this apple under normal bright light, you would see just an apple. But then if you start shining different wavelengths of light on this, you can see that there's bruising happening in the apple here. You can see, you can even use multispectral imaging to detect the ripeness of the fruit, the firmness, and also the pH levels, to see if it's ready to pick or if it still needs more time. For meat, you have on the right here, you have actually on the far right image, you have a bright field bunch of meat, and on the right, this is where you've actually hit it with different wavelengths of light to see your fat content versus protein content. On the bottom left here, you can see that this is turkey or some meat under bright field. And on the right half of that image, you can see that there's actual issues with the packaging, and you can see oxygen has been spilling into this meat packaging, which can't be good for its shelf life. You can also detect pesticide residues within meat or within your fruit or plants. You can spot contaminants as well as pathogens in some examples. And in the bottom image here, you can see that you have meat mixed with a bunch of fat and wood and plastics, which can't be good. Again, a few more examples here of bright field versus what you can see using near infrared or using hyperspectral or multispectral imaging. On this one, on the left here, we are looking at some cotton. It's claimed to be cotton, but if you look at the bottom left of this image, you can see that it's plastic and not exactly pure cotton. And on the right, you can see the apple on top under visible illumination and apple with bruising under short wave infrared illumination. So just the last slide here, you can see examples of, and it's essentially quality control, contamination, and sorting of the example with the walnuts here is under bright field. They look like just normal walnuts. But when you hit it with different wavelengths of light, you can see if there's contamination of shell or if there's contamination of any other products in the packaging. And on the left here, you can see your tea leaves. If they're undried, that can't be good for its shelf life. If it's too dry, that would affect the quality of the actual tea. So hope this was a good enough overview to show you the different applications of how multispectral or multiplex imaging can be used in sorting of different industries as well. Over to Gerhard. Thank you.
Thank you, Kavita, for this nice overview in using different illuminations for multiplex imaging. And welcome from my side to this webinar as well. I would like to have a look to the detection part of this multiplex imaging. And I would like to start again with the overview of the spectrum, because certainly for each of the applications, it's interesting to be aware that for different spectral parts, you need different types of detectors. Fortunately, with the different technologies from silicon to indium gallium arsenide and others, it's possible to really span the range from deep UV down from 2 nanometers up to 1700 nanometers, or even into the infrared to 12,000 nanometers. Before I come to examples, I would like to start with the general issue that you have if you want to create such a detector. So we are relying on the inner photoelectric effect that you might have heard in your high school time in physics or later on at the university. So we are always, with multiplex imaging, are relying on the interaction of light with matter. And if the energy of the light is enough to be absorbed in the matter, and the energy is high enough to elevate the charge carriers over this band gap, then we might use of the information. Here in this graph on the right-hand side with a curve that is in orange, you see the absorption coefficient of silicon along with the wavelength on the x-axis from 400 nanometers up to 1000 nanometers. And you see that the absorption coefficient is going down. And at the same time, the penetration depth is going up. And this has an impact on the design of these type of detectors and image sensors, which means that the absorption for blue light, like 400 nanometers, is very high. Therefore, the relevant sites that are able to collect charge carriers that have been generated by this radiation have to be near to the surface. If you are more looking into near infrared, then the penetration depth is larger and the absorption coefficient is smaller, and therefore you might want to place these volumes where the charges are collected deeper into the silicon. And here you see the proper penetration depth. And there is one parameter that describes the sensitivity of this effect, and this is the quantum efficiency. And the quantum efficiency is influenced by a couple of different things. If the photons arrive at the surface of the semiconductor material, then part of these radiation is reflected. So there's a certain loss due to reflection. Therefore, manufacturers of these image sensors try to improve the anti-reflective coatings such that as much radiation is hit or reaches the semiconductor. Then you have the area or the volume where the photons are penetrating into the semiconductor material, and part of the radiation, I mean the long wave part, is then transmitted through. You don't have to be aware of these equations, but here you see some real world results, and they prove what has been shown by the textbook graphs. And these are results from solar cell measurements. And again, the blue curve shows the absorption coefficient from 300 to 1400 nanometers, while the penetration depth is the red curve, which is increasing towards the 1400 nanometers. And in addition to that, the reflectivity of silicon is shown. So these are the influences that designers of image detectors or image sensors have to optimize and balance out depending on the application. Usually, manufacturers of image sensors and as well camera manufacturers try to give you this information by properly measured quantum efficiency curves, such that in advance, if you know your application has a certain requirement to have absorption, for example, in the visible, or to have absorption in the near infrared, then with these curves, you might be able to select the proper detectors or cameras that could do the job for your application. Here you see some examples from upper left, a silicon image sensor, and then another silicon image sensor, which includes the transmission of the entrance window. Because if you take a camera, then the QE curve of the image sensor is not enough. You need to know the QE behavior of the whole system. And therefore, it's fair enough to include the behavior and transmission losses of the entrance windows. And their performance, you see with a glass transmission on the upper right, can depend on the purpose for which the entrance window was designed. You see the blue curve with a lower performance, a lower transmission in the visible, but with an extended transmission towards 200 nanometers to the UV. So if you want to have a UV camera with this entrance window, then the blue curve is the one to go for. But if you are sure that your application only happens to be investigated in the visible range, then the green curve gives you a much better performance because it's lower transmission loss. Second, as you see on the lower left, there are sometimes different sensors of the same type, which might have a different anti-reflective coating or some other ingredients that help to improve the quantum efficiency, for example, in this case, towards the near-infrared. Finally, there are also sensors like the G-Sense 2020 BSI Pulsar with a different surface treatment, and this allows, like shown here, the sensitivity down towards 2 nanometers. The overall quantum efficiency is maybe worse compared to the visible part, but nevertheless, now the sensitivity goes down to extreme UV or soft X-ray. Another potential material for these type of image sensors is indium gallium arsenide or silicon sensors with an additional conversion layer made of quantum dots. And here you see some curves, and there is one sensor made by Sony, upper left, made of indium gallium arsenide, and this shows a very nice sensitivity from the visible towards 1700 in the shortwave infrared. The typical InGaAs sensors, like the one example from Xenix, usually are sensitive between 900 and 1700, while the different varieties of colloidal quantum dot sensors show a sensitivity from visible to SWIR, but usually at a much lower quantum efficiency compared to InGaAs. Well, if you use these type of cameras for multiplex imaging, then certainly there is a question whether you are doing hyperspectral or multispectral imaging. And the difference is for multispectral that you're not using the whole spectrum, but single responses at certain wavelengths, either defined by illumination or by a proper filtering. If you are going more for hyperspectral imaging to collect more information, then in most cases, if an array type of image sensor is used, then the image sensor is turned into a hyperspectrally resolved line scan sensor. So in one direction, you get the spatial information, while in the perpendicular direction on your image sensor, you get the spectrum. And for the type of investigations, you either have to move the camera or the sample to get for the whole image the hyperspectral information. But let's come to some examples. One example, and I mean it's about quality control, is certainly food sorting. Here it's an example given by a company called Headwall, who did these almond sorting machines, and their request for camera features was low readout noise, low light sensitivity in combination with a good linearity and a high dynamic range, and sufficiently enough resolution. And this could then be coupled with a faster conveyor speed, as well as having the possibility to get multiple information independent of the position of the almonds. Finally, they achieved with the two-camera system a high accuracy in detecting. Again, two different images from these applications. So this was a hyperspectral readout with a broadband illumination. And finally, the reflected light has been split up by a hyperspectral splitting. I guess it was grating they used. And then they have certainly for the application analysis software that does the job of the sorting of the almonds. Another potential application is in smart farming for plant classification. In this case, this is a research project which heads for differentiation between weeds and crops. If this could be done by a multispectral readout, then it would be possible by mechanical or optical means to destroy the weeds instead of using pesticides. In this combination, there was a shortwave infrared camera used, and we were going for a multi-band illumination with various LEDs at various wavelengths, and it included a broadband optics. The wavelengths ranged from 600 nanometers up to 1500 nanometers. And the goal was really to, if there is any kind of spectral fingerprint that allows to separate the weeds from the crops. And therefore, the plant samples were used in this industrial microscope setup that will be maybe more discussed by Michael, because it's as well a very nice system which has been optimized for shortwave infrared readout. And with these multicolor images, there are different possibilities of analysis. A classical thing would be principal component analysis. In this case, we've used a supervised learning algorithm, which is based on a random forest classifier. Usually you have this image stack and then you mark certain different areas. So in this case, the different plant samples, and try to get a good result with the analysis. And this was done. And we compared different measurements and different samples. But finally, we did all the measurements with 6 different wavelengths, which we considered as too many for practical application. And therefore, we tried to reduce them and did some different combinations and tried to figure out which is best using a random forest classifier. And we figured out that the combination of 625, 940, 1200, and 1550 nanometers worked best for us, which is shown at the different plant samples here. And this is still work in progress because the project is still ongoing, and this camera and this technology will be applied in a plant container to be sure that it later on can be used in the field. Another possibility and different modality is, for example, used wood classification. In former years, you would have to pay for getting rid of used wood in Germany. Nowadays, you get maybe money for it because it's considered as a source. Here we don't have a multispectral readout, but we are recording the fluorescence intensity and the fluorescence lifetime to do some classification processes. Therefore, we have a single band illumination using a bandpass filter, broadband optics, and have a dichroic mirror and emission bandpass filter and a proper camera that is able to measure the fluorescence lifetime. Here you see 2 examples of different woods, and the false color readout shows you the different lifetimes. And the motivation for this project was based on measurements that look with different plastic materials, because it's interesting that in the spectral range, the different plastic materials show different lifetimes, although the brightness, the fluorescence intensity, looks pretty much the same. And during that project, we used a setup with a robot arm to load the piece of wood onto the space of the area where the measurement has been taken. And due to some AI-based classification algorithms, it was possible with a better classification success of 90% to better sort the used wood, because there are different classes, and the first 2 classes can be used for further processing, and the rest has to be simply burned. Another possible application is the use of electroluminescence, because you might know that solar cells, if they are operated in flow direction, they emit electroluminescence. This electroluminescence, unfortunately, is in the range of above 1100 nanometers, and therefore it's not visible for typical silicon-based cameras. But if you use one of these shortwave infrared cameras with an InGaAs sensor, then you can get both the broadband illumination image to show the structure of the solar cell, as well as the electroluminescence. And the areas that do not show electroluminescence, they are dead. And this means, in turn, they do not produce or generate any current if sunshine or if sunlight is falling onto them. Therefore, it's a good method to do quality control in solar cell manufacturing. Another shortwave infrared application, as Kavita already has shown as well, is, for example, in food packaging. Here you see a sample of rice and some plastic rice pieces should be the example for maybe plastic pieces that fall into the rice during packaging. And again, we have a multi-band illumination with various LEDs at these wavelengths. And then we are learning, or we use a random forest classifier and train it and try to figure out. And as you can see here, marked in red versus green, the red is the plastic, while the green one is the natural rice. This works quite nicely, and we've shown this on some of the exhibitions where we've shown these systems in the last time. Another issue with food packaging, and as well Kavita has shown from one of these examples as well, is the separation or differentiation between walnuts and shells. In the visible, as you might see down there on the broadband illumination image, it's not that easy. It might be possible as well to do kind of a structural analysis, but it's a lot easier if you use the spectral fingerprint. And here we have used 6 different wavelengths to work on the analysis from 600 to 1450. And here you see the results with the principal component analysis or random forest classifier as well. This is something that can be done quite reliably, just with these typical analysis of multispectral image stacks. Now I'm finished with my part, and I would like to hand over to Michael to do the multiplex optical thing.
Great. Yeah, thanks, Gerhard. So as Gerhard and Kavita talked about, there are many benefits to using wavelengths outside of the classic visible spectrum. And today I'm going to talk a little bit about the aspects related, a bit of the theory and the design and manufacturing of optics for these kind of multi-band solutions. So certain things that you need to consider or think about. Okay, so basically fundamental to the design of any lens system is really starting with what wavelength band it's going to be used for. It's really the initial starting point for many of the impacts and many decisions that are going to happen downstream with the optical design choices. So with this information, it will typically drive the optical designers to select certain materials, coatings, or even specific design forms. It's really a fundamental starting point of any optical design. You can consider first like a single wavelength or waveband, so in the UV or the vis or near infrared, or you consider an extended band, so you're including the UV plus the vis or the vis plus the near infrared, or you consider a very broadband system that covers, maybe from the UV all the way to the near infrared or shortwave infrared. Now, generally speaking, if you extend the operating band, the complexity of the design increases. This also drives up the cost of the lens itself. So there's increasingly more benefits to consider multi-band solutions, as was displayed previously. The design and cost should be kept in mind because it is often exponential with optics production and manufacturing. Okay. So for multi or hyperspectral applications, basically what Gerhard pointed out is that we want to collect spectral information across a range of wavelengths and then form a spatial fingerprint, ideally on each individual pixel. So in an ideal system, you want to perfectly map the information for each wavelength from the object exactly to the corresponding location on the image plane for each wavelength. Ideally, you want that to be perfect. But in reality, we know there's no perfect lens, and you have to deal with some type of imperfections. So first, you have the effective diffraction. So essentially, light behaves as a wave. And as waves pass through any kind of opening, they will diffract. And the amount of diffraction is directly related to the wavelength. And it also determines the smallest size a spot can be focused to. So if you have a very broad wavelength range, the long wavelengths may spread out over more pixels compared to shorter wavelengths. Then you have aberrations, and this is really due to manufacturing and some design concerns of the lenses, and this will cause the light rays to not be perfectly focused to an ideal pixel location. So they could be shifted left, right, up, down, or longitudinally as well, or other types of aberrations that can ultimately impact the image quality. And then finally, we have environmental considerations, and it is important to consider things like thermal effects, vibration, shock, and even altitude changes sometimes, because this can impact how the light rays from the object are ultimately mapped to your pixel location. Good. So a little bit some fundamentals from optics. So basically, as light rays pass through a lens, they are ultimately governed by Snell's law, and this determines basically how the rays are going to be bent through the lens. It depends on the material's index of refraction and the angle of incidence that the light hits the interface itself. Now, in an ideal world, the most natural shape of a lens to bring light rays to a perfect focus would be aspherical, and this is shown at the top right of this image right here. However, for aspherical surfaces, it's typically they have manufacturing challenges, and it's hard to make them economically in batches. So in most cases, it's actually more beneficial to produce spherical shaped lenses. It's more economical, and you can manufacture these in larger batches at a more effective cost point. Unfortunately, with the spherical shape, it is not perfect, and it will cause rays to refract in not the most ideal way. And what happens here is what is called spherical aberrations. And one of the problems is as the angle of the ray striking the surfaces gets larger and larger, it introduces more errors. And this is shown on the table at the bottom right here. So as you can see here is when the angles get very, very large, like you have angles of incidence of 30 or 40 degrees, you have very large errors. Now, typically optical designers, they can use spherical lenses and they can add additional lenses to help correct for this. But it gets increasingly challenging and difficult to make a design when the angles get steeper and steeper. And in fact, it's almost essential if you really want to have a well-corrected lens that you really minimize these angles for very high performance lenses. And I'll show an example on the next slide here. Great. So for a very well-corrected lens like the lithographic lens that's shown here, basically what you can see is that the lens shapes are bent to follow the natural flow of the wavefront itself. So you'll see some lenses that are bent towards the left, some that are kind of symmetrical about a central vertical axis, and some that are bent towards the right. And really the goal is here when the optical designer is making such a lens is they want to minimize the angles of the rays that are striking each individual surface for the point that was mentioned before to really reduce the aberrations. And if you have a really well-corrected lens like this, the end result is the rays will look like they're smoothly flowing through the entire system. It's almost like you're watching water flow slowly through like a slow-moving river or something. So it's a very gradual, smooth flow without any kind of major changes in direction, abrupt changes in direction. So the next challenge is that glass actually has dispersion, and this means that the index of refraction changes with the wavelength. So depending on what your wavelength of light is, the rays will be bent differently and focused at different locations, both longitudinally and laterally. And this is a challenge for spectral applications where you want to map something exactly to a pixel. So this becomes more complex for broadband systems, and the designers may need to use really special glass types, like really low dispersion glasses, or different design techniques to help compensate for this. Now, an additional challenge here is that many times different glasses, the index refraction will also change with temperature. So you basically have to combine all these different effects, like with the index refraction that's dependent on the wavelength, plus the temperature, plus the things that were mentioned before, and compensate all that. You can get a very complicated design if you have a broadband operating wavelength that you need to address. So some kind of multispectral considerations. We talked about this a little bit before. So when considering a lens choice, it's really important to consider one that is designed for this purpose. It's often a little bit more complex, but it is necessary to achieve the results that you are required, based on the slides that were mentioned before. If you don't necessarily consider these things, you're going to have poor performance, and it might not deliver the experience or the results that you're hoping to achieve. Transmission can also be a concern, and this is both for AR coatings and also the glass selection itself. So a lot of glasses in the UV, they have strong absorption bands around 350 or 375 nanometers. And additionally, AR coatings, they get increasingly difficult for broadband solutions. And you want to make sure ultimately that the light for each wavelength you're interested in is passing through your lens in the most uniform way, ideally. Straight light can also be a concern, and sometimes with longer wavelengths or different wavelengths, you have to consider different techniques. So you may use different materials or baffling designs that have to be taken into consideration so that these won't impact the quality of your image. And in some cases, you may also have to have pupil matching or attendees. And essentially, this is when you have one lens system that is being coupled to another lens system. Say many times there's a spectrograph that's used for a hyperspectral camera. And if you don't properly match the pupils, the exit pupil from one lens system to the entrance pupil from another lens system, you may have unwanted vignetting effects occurring. So these are things that sometimes you also have to consider. Then we also discussed a little bit the environmental impacts, so the temperature changes and the vibration, these things. And ultimately, you have to consider the cost and performance trade-offs and what's really important for your particular application. Good. So now a few quick examples. Good. So aerial imaging is an area where there are lots of benefits for multispectral imaging. In this case, you would have a broadband source, which is ultimately the sun, and it's shining down on your sample, which is the Earth. And you want to collect the reflected light at different wavelengths and ultimately deliver those to your camera system. So it could be a visible, a vis sphere, or several cameras that are capturing this information at the same time. And by looking at wavebands outside of visible range, you're able to collect more information than just high resolution details, which is shown in the top right here, which is very important for an aerial image where you want to capture as wide a field of view as possible, but still resolve fine details. One area of interesting, which is related to what Gerhard also mentioned, is monitoring crop or soil health. So if you consider looking at both the visible and near infrared channels, typically you can form some kind of an index, it's called, and it's a summation of different wavelengths, typically visible and near infrared. And you can monitor this combined reflective index value, and you can monitor the kind of the plant health. So it can tell you different things about the chlorophyll in the foliage and soil health and stuff. Another benefit is for shortwave infrared. Due to the scattering properties of light, it can actually penetrate deeper and further through fog and smoke. And this could be an invaluable tool, say for like a wildfire, where you want to identify exactly where the source of the fire is coming from. And by using shortwave infrared, you can actually penetrate through the smoke and identify where that is coming from. Spectral information also allows you to get more information about the material and the mineral identification. This is shown on the bottom right here. This is of interest for areas like surveyors where they're looking for mineral deposits, or insurance companies where they want to know what materials certain things are made of. And this is all kind of interesting applications where multispectral is very beneficial for aerial type applications. Another area is related to the inspection of flat panel displays. So in this case, you're using UV light and you're inspecting flat panel displays like micro LEDs. Now with ordinary light, it's not always easy to detect the defective pixels. But if you do use UV photoluminescence approach, you basically have another mechanism to detect defective pixels. So in this case, the UV light is not being used for imaging, but it's rather being used for excitation. The emitted light is then collected, and the image the image in the visible light is collected, and it provides additional information that was not ordinarily present with the visible wavelength. So you can get information about the pixel intensity, or if there's cracks there. And by doing this, you can kind of sort out and calibrate different individual pixels on a panel. So in this case, the optics, they should be able to transmit high power UV light to the sample, but not necessarily be used for imaging purposes. Okay, so at Excelitas, we have a really wide range of lenses that are available. They go from kind of classic wide field of view lenses all the way through micro inspection solutions that can detect the smallest features. And selecting the right lens for your application is very dependent on your application. And it's often challenging to know where to start. Now, if you typically know a few basics about what you're trying to do, so what's the working distance, or what's the object size, or the sensor size, and then if you consider a few other things that were discussed before, like the spectral wave band or the resolution, depth of field, then you have a good idea of where to start. And we have built a tool called the MockViz Machine Vision Configurator. If you take some of these inputs and input them into the MockViz Configurator, it's going to give you a recommendation of what camera and lens that we offer at Excelitas that could potentially be a good fit for your application. So I would highly recommend this. Is a great place to start. It's a really good tool that has many features in it to help get started with your application. And then we're always there to help provide guidance as well. Then in terms of Excelitas, so here's a couple of lenses that are showing some of the multi-band capabilities from a lens perspective that we have. So, at first we have the Optimum Fusion Sphere. So this is part of a modular microscopy platform, and this lens system was designed to image from 633 nanometers to 1700 nanometers. And this is kind of like a near sphere solution that can be used for applications in this area. And one typical example here is for the semiconductor area, where you want to image through silicon, and that's possible with wavelengths that are longer than about 1100 nanometers. Then our newest addition, which is shown in the middle here, is the Inspect XL Vis Near lens. This is a large format, high resolution line scan lens that's designed for wavelengths from 400 to 1150 nanometers. This is the newest addition, and it supports these large sensor sizes for line scan applications. And there's applications we see in again in the semiconductor area for substrate or PCB inspection. We're also always happy to discuss customized solutions, and we can customize a solution in a build to spec or build to print type scenario, or even a modified off the shelf solution as well. And it can include illumination, sensors, and optics all in one kind of sub assembly essentially. Great, and this is an example of a multiplex solution that we're showing here. And this is the same setup that was used for some of the imagery that was presented by Gerhard as well. And it consists of several components. So it consists of the Optimum Sphere microscope with the zoom lens that we mentioned in the last slide. It also has the PCO Pixelfly sphere camera, and also a multispectral LED ring light. And if you combine all these together, these different specialties from Excelitas, each one of these areas, you can form a very flexible imaging system that can be used for these different applications that we're discussing. Great. And Yeah, finally, so Excelitas, we have experience in designing and manufacturing illumination, cameras, and optics. And, we always welcome a discussion with you and see how we can support your application in any one of these individual areas, but also combined as a full imaging solution. So this idea of a multiplex toolbox and having each individual component, but also combine them as one full system and providing that, that help for you in finding the right solution for your application. We're always willing to talk to you and see what we can do to help support you. So from that, my part is also finished, and I want to thank you for attending the webinar and your time. I do hope it was informative.
Some of you have already submitted some questions, so we're just going to jump right in. As a reminder, if you would like to submit a question, please type your question into the question window on the side of your screen and hit the submit button. Also, please, if you would, stay until the end of the presentation to complete the exit survey, which will pop up on your screen. You can preview the questions now by clicking the exit survey icon on the left side rail. Okay, let's go ahead to these. First off, what sensor can differentiate metal, object, and rocks or in mining industries?
Well, that's certainly a very good question. But since I'm not in the mining business, I don't know about the spectral behavior of the different materials. So if you could give me some absorption, reflection, or fluorescence spectra, then I could answer this question, because in general, it depends whether the spectral absorption is more different in the visible or in the near infrared or in the shortwave infrared. This is something I don't know by experience.
Okay. All right. For which applications is it better to use broadband compared to multi-band illumination light sources?
So I can take that one.
Yeah.
It's essentially, excuse me, broadband will do the job just fine. If there's an application where you need to switch very quickly between the different colors, if you're doing something high throughput or something you need to get through a lot of samples in a certain amount of time, then you would go with multiband, and you would use be able to switch quickly between the colors and get your signal faster. You wouldn't have to rely on a filter wheel to filter the light, basically.
Okay. For all different spectral ranges, UV, VIS, NIR, and SWIR, do I need a different set of optics? Or do I need different optics?
Yeah, so I can handle this. So, as was demonstrated before with some of the slides that I talked about, it depends on what you're trying to achieve. So in an ideal situation, if you're only looking at one individual band, say if it's the UV, VIS, or NIR, then it's probably better to focus on having specific lenses for that that are designed and optimized for that wave band. So in the UV, for example, you have specific glasses that may only be able to transmit UV wavelengths, and those ones they kind of limit the choice that optical designers have when designing a lens. So you may not want to use those type of optics when considering a visible or infrared solution. However, if you are looking for a really broadband solution with many different wavelengths, then you may want to consider one lens that can cover a broader band. So I hope that answers the question.
Okay. Is quantum efficiency the only important parameter in low light imaging?
Well, I don't think so, but it's a major one, because if you're going for multispectral, then in general, first is you will have to have a detector that is suitable for the application. Second is, since in many applications and with different filters, there might be a larger difference in the signal quantity, and therefore I would say a larger dynamic range can come in handy. Additional parameters like readout noise are important if you're going more to fluorescence imaging, because in general, in most of the fluorescence markers application, or very many fluorescence applications, are restricted to very low signals. I just have taken the spectral sensitivity as one of the major parameters.
Okay. What's the difference in using a broadband illumination and color camera compared to multi-band illumination and using a monochrome camera?
I would say resolution. Because in general, if you take your actual smartphone cameras, then they have different color filters on each pixel. So most popular is the so-called Bayer pattern, which has 2 green, 1 red, and 1 blue filter, set of 2 by 2 pixels. Therefore, the real resolution is a third of what the number of pixels is. If you switch to changing the illumination, then you can use the full resolution. Therefore, if you use a switching illumination and a monochrome sensor, then you get a higher resolution for your color images.
Okay. Could you handle a mid-scale building size with multispectral illumination delivered from a high-power source via optical fiber combined with appropriate camera systems?
I would say yes.
Okay.
But well, what would you say, Kavita, concerning the illumination?
Well, a building, chances are it's not with an optical fiber,
Okay.
unless it's a really massive optical fiber. But
Okay.
yes, if you're looking at sunlight, or if you're using a large illumination source, absolutely.
Okay, great. Well, I'm afraid we've run out of time. For those questions we didn't have time to answer, we'll be getting back to you via email. That concludes today's presentation. On behalf of VSD, I'd like to thank Kavita, Gerhard, and Michael for their presentation today, Excelitas Technologies for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day.